All right, let's have a bit of a recap of Cartesian geometry and a couple of formulas that we should be very familiar with, but certainly comes in useful. One, the distance formula. How do we find the distance between 2 points on a number plane? And it essentially is Pythagoras' theorem, if you think about it. D could be thought of as the hypotenuse of a right-angled triangle. You could create a triangle. The other sides would then be the difference in the x values and the difference in the y values. So if we wanted to find the distance, plugging it in, and there we go, we get 2 root 5 for that particular one. Okay, so to say, it's basically Pythagoras' theorem. The other one that's very useful, of course, is midpoint. How do I find the point that's in the middle of another 2 points? Now, essentially, what you're doing here is finding the average. Because how do you find something that's in the middle of? Well, you find the average. And that will end up what's in the middle. And we do it for both the x values and the y values. So for this one, add them together, divide by 2. There's our midpoint. So why on earth am I talking about Euclidean geometry before? What was the point of mentioning it? Because geometry is geometry. And okay, we might say there's Cartesian geometry when we look at the number plane, and there's Euclidean geometry when we look at angles in a triangle and all that sort of thing. But it's all geometry, and there's no reason why we can't use Euclidean geometry to solve Cartesian geometry problems. So all those theorems that you learnt in the junior school still can be very useful in solving, say, a Cartesian geometry problem. So I think one of the key ones is quadrilaterals. So classifying quadrilaterals. Quadrilaterals, we classify them by the features, and the more specialised the features, then we can narrow down the type of quadrilateral that we may have. And so there's the little family tree. Starts there with a quadrilateral, which of course is just a 4-sided figure, but from there we can branch off and get to the other quadrilaterals. Now, the thing is, any property you know about a particular quadrilateral can be used for anything that branches into that quadrilateral. So, for instance, you could use theorems about the parallelogram if you know the shapes of rhombus, because a rhombus is a type of parallelogram. The example I've got here, a rhombus, there you go. But not only could I use parallelogram, I could use any feature about a trapezium, a kite, a quadrilateral, any of those ideas I could use. So let's break it down. Quadrilateral. What do we know about quadrilaterals? It's got 4 sides. Probably not that useful. It's got 4 angles. Yeah, still probably not that useful. But other than that, it pretty much hasn't got specific things. Other than, all right, we know it's a quadrilateral. But it branches off. Let's go over to our kite. The kite is the one where adjacent sides are equal. So a pair of adjacent sides, so you get that traditional kite shape if you think of a kite. The interesting fact in a kite is the diagonals will always be perpendicular. They'll always be perpendicular to each other. And now, whether you realise this or not, the area of a kite is a half xy, where x and y are the length of the diagonals. Now, you most normally associate that with a rhombus, but it's not actually the formula for a rhombus. It's actually the formula for a kite, but a rhombus is a type of kite, and that's why we can use it for a rhombus. Okay, let's branch out the other side to a trapezium, and that's where we have one pair of the sides are parallel. Don't know a heck of a lot, but we do have an area formula for it. We know half the height, that being the perpendicular height, and then the sum of the parallel sides. Okay, let's branch down to the parallelogram. So a parallelogram is a type of trapezium, so I suppose theoretically you could, if you wanted to, use the trapezium area formula to find the area of a parallelogram. Don't know why you'd want to, but you could. It's now got 2 pairs of parallel sides. Opposite sides in a parallelogram are equal, we know that. We also know opposite angles in a parallelogram are equal. The diagonals bisect each other. And the area, the specific one for parallelogram, is base times the perpendicular height. Now, if you wanted to prove a shape's a parallelogram, yes, you could show these features, but there's an additional one. If you only know information about a pair of opposite sides, but if you can show that those opposite sides are both equal and parallel, then it must be a parallelogram. Now, kite and parallelogram. So parallelogram are going to branch off to rectangle. So what additional information have we got? Well, the angles now become 90 degrees in the shape. Now the diagonals become equal. And length times breadth is our area formula. Okay, rhombus, which comes from both the kite and the parallelogram. So it has all the features of a kite, all the features of a parallelogram, and this additional piece of information now is that the diagonals will bisect the vertex. Okay, the square, the perfect quadrilateral, it branches down eventually from all of them. So any feature of any quadrilateral can be used with a square. What additional information do we know? We know the area is s squared. Hence the name of the shape, I suppose. All right, so let's have a look at a question here. We've been given 4 points. They form a quadrilateral. We want to show the shape's a rhombus. So we've got to pull out some facts we know about a rhombus. So I'm going to find the midpoint of AC. Turns out to be 5 on 2 minus a half. I'm also going to find the midpoint of BD. And I notice the midpoints are the same. So that's telling me the diagonals bisect each other. Well, that's enough to tell me that the shape is a parallelogram. So I haven't quite got that it's a rhombus yet. So additional information that will make it a rhombus. I've got a parallelogram. I want to make it a rhombus. I could show, what could I show? Well, we know all the sides are equal in a rhombus. Could that help me? We know the diagonals bisect the vertex. Ooh, that could be a bit tricky to show on this one. Which way did I go? What have I done? Let's have a look. I found the length of CD, so it looks like I'm going with the sides here, and it's 5. The length of AD, it's 5 as well. That's now all I need, because what I've now actually shown is that it's a kite, because the adjacent sides are equal. So we now know ABCD is a rhombus because we've shown that it's a parallelogram, but it also has the adjacent sides equal. So it's both a parallelogram and a kite, therefore a rhombus. Okay. We shall play around with that for today.